My name is Sergio Lizalde. I'm the chair of the math department, and I just wanted to say a couple of words about the Lahr lectures. So the Lahr lectures were established in 2020 to honor Dwight Lahr, who was a professor of mathematics here, and he was the first black mathematician to receive tenure in an Ivy League institution. And he was also very committed to diversity and inclusivity and to public education in the inner city. And we created this lecture series partly to bring speakers from underrepresented groups and also speakers who have done a lot of work in diversity and inclusion. And I will also say that Dwight was a great person. It was one of the first faculty members I met when I came here, and I had the pleasure to teach Math 3 with him my first fall here, and he was a great help. So I'm going to let Rosa Orellana introduce our speaker for today.
So before I introduce Pamela Harris, I want to say something. When I arrived, I think one of the things that is very important is community, like creating a community. And I have to say that Dwight did that for me here when I arrived. One of the reasons I came to Dartmouth, he was actually, I think, the chair of the hiring committee the year that I was hired. So I feel that, when I have nominated people to come and give this talk, now there are several, I always think of people who do a lot for the community. So having said that, I want to introduce Pamela Harris, which I admire tremendously for all the work that she does to create a mathematical community. And this is, I don't say it, just to say it. I mean, she's very highly recognized for all the work that she does. Right now, she's an associate professor at the University of Wisconsin at Milwaukee, where she got her PhD with one of my ex-colleagues as a graduate student at UCSD. So she's kind of like, a student of somebody that I knew very well through graduate school. She's the founder of the platform lattice, which is kind of like tries to kind of highlight mathematics in the Latin community, but not only the mathematical community. She does like for the LG, the LG. BTQ plus. She has organized things for that for African Americans. She's doing a lot for the community to bring inclusion at every single level. She is an editor of the AMS e-mentoring blog. I mean, it's kind of like, a lot of people talk a lot about mentoring, but very few people actually do like the work on the mentoring. And I think Pamela is somebody who actually does that. I mean, she doesn't only talk about it, or like she actually is doing a lot of the mentoring, and she has been recognized. She has received like countless awards for teaching. And for example, she received the Mathematical Association, American Association, the Henry Alder Distinguished Teaching Award. She's a fierce advocate for diversity at every level, including inclusivity in mathematics. She's an AMS fellow, an AWM fellow. I mean, like highly recognized for all the effort, and she's an amazing mathematician. She's only an associate professor on leave from Williams right now. She has over 60 publications already, and what speaks mostly about this is that she has like around 150 collaborators. Like, I mean, and I'm lucky to count myself as one of them. but it's kind of somebody who does, we are organizing a workshop for young mathematicians. So if you're in the area of combinatorics, look at the AMS announcement, right? The mathematical research community through the AMS. But it's somebody who's like endless energy and like organizes so many things and tries to include, has served for, done countless REUs, even, did things online when things couldn't be live, and everybody loves her. So I'm kind of like including myself. So I'm very happy that she's here for us, and she's going to tell us about how to choose your own mathematical adventures. So here is Pamela.
Wow, so I really tried my best to not tear up, but I still had the where's the tissue? We didn't talk about the tissue. Thank you, seriously. I count myself very lucky to get to work with you. So thanks everyone for the invitation. I'm super excited to be here. So for some of you that were at the earlier talk, you will see some favorite combinatorial objects of mine reappear. But before we do that, I want to tell you a little bit about what the plan for today is. So the first thing is I do a lot of research, and I love introducing students who are like, what, math research? You don't mean, everything's known, right? All the math is known. It's all in this book. And I'm like, let me show you new things. So I want to talk about what does it look like to do mathematical research, because I'm not assuming everyone in the room knows what that entails. And I also want to think about how does one actually decide what it is that you're going to work on? And so earlier in the previous lecture, we kind of hinted at that at the end. How do you come up with questions? How do you know that that's the thing to do? How? So that's a main motivation for today. And then, as Rosa pointed out, I do a lot of collaborative work. For me, mathematics is more enjoyable when I have good people to talk math with. And so I want to talk about how I've been building mathematical collaborations in a lot of the work that I do. But also, the thing is, I want to tell you about some of these math projects that have been really cool and have led to some unexpected results. So we'll focus on these three things. And so I'll tell you about lattice point visibility, which I had never heard of until somebody introduced it to me. Oh, the number theorists in the audience are like, yeah. Okay, so I am no number theorist. But all of a sudden, I find myself, doing some stuff with lattice point visibility, so we'll get there. And then some of the combinatorics of parking functions. And then the thing that I know and love is these vector partition functions. And I want to tell you what I told my parents, all I've been doing is juggling. And they're like, what? And I was like, never mind, it's not that interesting. But basically, all the PhD work that I did, it took me maybe 10 years or so to recognize that all I was doing was actually mathematical juggling. So I want to show you some of that. All right, so the first thing is, who am I? And I think that's an important question when you go to a talk, okay, all right, so I have a PhD, I'm a mathematician, all of these things, but it didn't start out that way, right? So at some point, I was a little girl, and I was born in Guadalajara, Jalisco, Mexico, which is where this little star is. And very early on, I kind of liked math, but I didn't really pursue much of math, so I wasn't a kid that went to competitions. My parents didn't graduate high school, so we didn't have conversations about cool math, intriguing puzzles, or anything like that. It was more just do you know your auntie's phone number so that if you get lost, you know who to call, right? So a lot of my early childhood memories about math were just can I memorize as many phone numbers as possible? Because I was a wanderer. Were you a wanderer when you were a kid? Where you were no, you didn't wander? You weren't walking around somewhere in a market and just a dog, and then go that way and run? Okay, maybe not, but I was, and so that was why my parents made me memorize tons of phone numbers. But very early on, we moved to the US, mostly for the same reason that a lot of people moved to the US, for the chasing of the American dream. I can tell you that San Diego was very sunny, but it also was very expensive. And so very quickly we recognized that living in a basement, you should think about what I'm saying, because it's California. How many houses do you know have basements? If you know California, not many, right? Like, so living in a basement in a house in California was not an ideal situation, to say the least. Like, it was a room, it had dirt floors. Like, I'm talking about California, right? Not like a third world country. This is where we lived, right? A 1-bedroom apartment, me, my brother, my mom, my dad, my uncle. And my parents were like, that's not the American dream that we envisioned. And so we shortly returned to Mexico, and then my father had family in Wisconsin. And so his youngest sister, so my aunt, and his oldest brother, my uncle, were in Milwaukee, and they said, you know what? It's cold. There's lots of snow, but there are jobs. And so at the age of 12, we moved to Milwaukee, Wisconsin. And I'm kind of skipping ahead because I want to talk more about math in my life. But like I said, my parents never graduated high school. And so for me, I never thought about going to college. The bar that my parents set was, you finish high school at every cost, because by that time, you'll be the most educated person in our family. And so we never talked about going to college, let alone becoming a mathematician. Like, those were not at all in the realm of possibilities of my life. I also was undocumented, and I talk about that publicly a lot because I think there's narratives that you as young people hear about what it means to be undocumented in this country. And I want to just say that, we're not all here to steal anybody's jobs. We're here to work really hard and to hope that we have an opportunity to fulfill, our capabilities and hopefully achieve our dreams. And so, long story short, I began college at Milwaukee Area Technical College. And one of the things that I should tell you about is that I was not at all at a point in my life where math was going well. Like, I went to MATC and I had to do one of those like online testing, right? Where you're like or not online, but like on the computer testing to like kind of find your placement. And I placed into what is the equivalent of about 7th grade math. So like, I could not factor a quadratic. That was perfectly factorable. Like, I couldn't. I was like, I don't understand. What do you mean? And I knew the quadratic formula. Like, we had to memorize it, but I didn't understand when they said factor this, like how to do it. So I started exactly where I needed to. I took intermediate algebra. I took college algebra. I took trig. I took Calc 1, 2, and 3 at the community college. And then one of my professors said, you should go to Marquette University. And I was like, for what? And then he's like, to get a bachelor's in mathematics. And I said, okay. And then I was like, why, but why there? And he said, my father was a professor there, and I think Marquette is wonderful and is right down the street. And when I say right down the street, they're within, like, you can walk there in 10 minutes, right? So I was like, okay, fine, I'll apply to Marquette. And so I went to Marquette and I finished my bachelor's in mathematics. Still not knowing that like math was a thing that people did professionally. Like, I just thought the job you get is like, you go teach high school, right? Which was silly because I never even realized that my professors had that as a job. Like, I was like, they're just here for fun, which we are, but we also enjoy getting paid. Now, when I graduated undergrad, my personal life was at an interesting place. So my daughter was born, so I graduated in December. My daughter was born in April, and I started graduate school that August. And my husband, who instead of going to college, he decided at that point in his life what made more sense was to go to the military, so he became a Marine. And he was gone from February 6th, 2006 to February 7th, 2007. Note that Akira was, he was deployed to Iraq. Note that Akira was born in April. And so he missed her birth. But I had thought, if life isn't hard enough with a baby and a husband in Iraq, like, let's just go get this math PhD. And I should say that the only reason why I went to graduate school is because one of my professors at Marquette said, I was studying analysis, and it was the first time I ever encountered lim soup. And I kept saying in my head, lemon soup, this is awful. I hate all of this. I don't understand anything about convergence. Like, why does anybody care? And it was an independent study class. And so it was just me. I didn't have anybody to talk to except the professor. And during one of the meetings, she said, listen, don't worry. The point is that you're learning some of the concepts, and when you get to graduate school, you'll see them again. And then I just looked at her and I was like, what is graduate school? And then she said, oh, you go for your master's and your PhD, and most of the time they'll pay you money. And I was like, I like that idea. And so I went to graduate school simply because one professor said to me, when you go there. And so, yeah, so I decided, all right, personal life is in chaos. Yeah, let's throw in some math. And I just wanted to show you that I'm not kidding, like how close all of my schools were. So now at this point I have a baby and I'm still living at home, mind you. My husband's in Iraq. And I decide I'm gonna do more math. And so like, here's MATC in this little yellow box. And I don't know if you can tell, but it's like, 1, 2, 3, maybe 4 or 5 blocks. And then you get to Marquette. And then, okay, a few miles, but you get to UW Milwaukee. And so I never actually had to leave home. Like I got to do, middle school all the way through PhD, and no joke, the same city bus would take me to all these places. Now for graduate school, when she told me, oh, you can go to graduate school, I was graduating December. At this point, like I was done with my undergrad, so I had missed all the applications. I didn't plan, I didn't take the GRE. And I was like, well, I gotta stay home, so which schools have a PhD? And it was like, Milwaukee. I was like, great, I'll go there. And I applied and they accepted me. Yay, because I don't know what I would not be here otherwise probably. But I actually think about how lucky I was to go there. Because one of the things that I actually didn't realize until much later in my life is that universities do not tend to financially support parents. Meaning, you will get your own stipend, right? But they're like, if you have a kid, like that's your responsibility. We're not gonna pay you more because you're a mom. UWM did. They said, oh, you have additional expenses and responsibilities as a graduate student, so we're gonna put you on this particular fellowship where you teach less, and we're gonna account for your financial expenses as a mom because you have daycare expenses. And so I actually got additional stipend and teaching reductions because they were cognizant that there was additional barriers to my degree completion. I did not realize that schools didn't do that. I didn't realize that that wasn't normal. And so for me, it was a great program. And so here's, me and Akira when we graduated. I say we because, she was there the whole time. We made it together. So I PhD done. And the first job that I took out of my PhD program was a postdoctoral position at the United States Military Academy in New York. And I loved that job, so much so that I extended it as far as I could take it. I was there for a total of 4 years. But one of the things that was really interesting about this job is that they hire teachers, right? They want professors, not necessarily researchers. But I knew that I wanted to continue doing research. And so one of the things that I struggled with was, okay, how do I do this when the teaching load was so heavy? So the initial contract is 4 courses per semester, which basically leaves you 0 time to think about math at all other than grade. That's literally like every day was just grade constantly. And so I applied for this other position, which is the Davies Research Fellowship. And so I was able to teach half the time. So one semester I was teaching, and then the other I had for research. But now that I had the time, I was like, what am I gonna work on? Because I have to make the best of it if I'm gonna have any shot at landing some sort of more research active job. So here's the first thing I started thinking about. So I had one of my wonderful friends. So this is Abba here, Amma Babrika, and then Beth Kubek. So Beth was also a postdoc at the same time. And we invited Abba to come and give a talk. And so Abba talked about something completely different during his seminar. And we're at a dinner. And let me tell you, I love restaurants that have paper mats. Like, that when they just roll up the paper? Like, there was this Indian restaurant. It was fantastic. And so we go to this restaurant. And Abba starts doodling on the paper as our food is coming. And he tells us this story. He says, you've ever looked at the trees when you're driving on the road? And then there's that really cool moment where it looks like there's only the front trees, like all the other ones are hidden. And I was like, yeah, I relate. Okay, so he said, think about this problem. So suppose that I put, this tree, and all of a sudden it's gonna cover the ones behind it. And actually, this is sort of how they plant trees, right? Like they wanna sort of equally space them out. And he said, well, now put it on a lattice. So he said, what we're gonna do is we're gonna think about this part of the lattice, or just the positive quadrant. And let's imagine that we're gonna plop our eyeball, so we're standing right at the origin. And I'm gonna imagine that I have little trees, like infinitely thin trees at every little point on the lattice, so this integer lattice points. And you're gonna be able to see in straight lines, and so there's this like thing I can do where if you're right there and I just do this, I don't see the person behind you, right? So that's kind of the idea, that there's gonna be some tree I see, and everything after that gets blocked from my view. So let's put some trees, let's put some coordinates, and I want you to think, what will it block? So I can see the point or the tree at position 1, 3. What's behind it? What's behind it? 2, 6. What else? 3, 9. Okay, you're starting to see the pattern. What about behind 2, 1? Come on, I know you see it. Yeah. Or not. I don't know. Pun intended. Yeah, so 4, 2. 6, 3. What are you doing? It's following a line, right? So you're like, multiply the entries by 2, multiply the entries by 3, and so on, right? So that's exactly the things that get covered. So once you see a point, it blocks from view anything that's a multiple of it. Okay, great. So now the key is to try to figure out, how do I determine when a point is visible? Like when, if I'm standing at the origin, can I actually see such a point? So the answer is the following. So we're gonna talk about a point either being visible or invisible. A point is visible only when they share no common factors. So the greatest thing that divides those numbers is 1. So if you go back to the picture, notice I see 1 and 3 because what's the GCD between 1 and 3? 1, right? 2 and 1. 4 and 2 gets blocked because the GCD is 2. So this is a number theory question, right? When do I see a point? If and only if they're coprime. All right, great. So here's just the same picture again. So now here is a nice little image. So we colored all of the invisible points. What patterns do you see? If you stare at the dots long enough, you see some patterns, yeah? What do you see? Yeah, there's at least some sort of like diagonal thing that's showing up. What's that diagonal? Y equals X. So notice that right here, I don't know if you can tell, but there's no dot right here because this one is actually visible. So I'm plotting the ones that are invisible. That one's visible, and then it covers everything on that line. What do you notice about like some symmetry property? Do you see a symmetry happening across that diagonal? Can you see? The image mirrors across the diagonal. Why? GCD of X and Y is the same thing as GCD of Y and X, right? It doesn't matter which way I ordered the elements, the GCD is gonna be the same. And so if it's invisible on this side, it'll be invisible on this side. Yeah? So there's some nice properties showing up. Okay, so now the question is, and notice this is just, I think, 50 by 50. So one of the questions that we might care about is, what's the proportion of visible points? Somebody want to throw out a guess? The ones that know, don't say a thing. Throw out a percentage. This is the chance where you get to just be wrong. Ben, be wrong for me. What percentage do you think is visible? 60%. He knows more than he lets on. Okay. Oh, he was closing his mouth. Okay, great. Okay, so there's this actual real old result, 1881 from Cesaro, that says that if I just randomly pick 2 integers, the probability that they're relatively prime is 6 over pi squared. So, you know, lattice point geometers might say that then that means that the fraction of pairs x, y, whose GCD is 1, is about 60%. Not talking to Ben anymore. That was it. He ruined my fun. Okay, 60%. That's pretty cool, right? So 60%, if you're at the origin, 60% is what you can see. Okay, so that's the story that Abba tells us at dinner. Pretty cool, right? And we're just like, this is awesome. All right, so proof, exercise. Okay, so now let me tell you what happened. So we're at this dinner, and we've now at this point taken over that, and like we moved all our dishes out the way. We're like not even eating the delicious chicken tikka masala. And then I lift my glass, and I saw something like this. And I was like, Abba, what happens if the lines are curvy? Okay? Real simple question. And then he was like, curvy? And I was like, yeah, like a parabola. Like, what if instead of using straight lines of sight, you put a parabola? And it has to go through the origin, and you use some rational coefficient. Okay, like, start now, getting a little bit better at framing what I mean by using curvy lines. And then Abba says, oh, that's interesting. Well, in all the literature I've looked at, like, that hasn't appeared. I don't think anybody's done that. And I was like, well, we should try. So here's what we did. So the question is, what happens if the lines of sight are not straight lines? So come in somebody who I think this lecture series knows. So Edre Goins, the resident number theorist that I needed, because I was like, what is relatively prime again? No, just kidding. I knew that. I knew that much by now. But so, Edre was visiting actually, and so I introduced Edre to Abba and to Beth, and we started working on this problem. So now let's make this very concrete. So what I'm gonna do is I'm gonna fix a particular exponent. So that's gonna be a positive integer for me, so these start at 1. So I'm gonna fix the exponent of my power function. So my functions look something like rational number x exponent b. And now I'm gonna ask the exact same question. When is a point visible? When is a point invisible? Okay, so back to our lattice. So now I just wanna point out, so this is some line of sight that we would have used in the previous case. It's just a straight line. And then this is sort of the new thing that we're gonna do. So something like 2x squared. And notice what happens. So 1, 2 is visible while 2, 4 is not. Yeah? And then, okay, sure, they intersect. But over here, that's like the standard thing. So you see a point if it's relatively prime. But now this is not necessarily a thing about being relatively prime in the usual sense. So what we discover is that we can generalize the result of determining whether a point is visible or not with the following definition. So we were clever and we just put a little tilde on it, subscript b. So what we do is we look at the things that divide r, whose bth power divide s. R is the x coordinate, s is the y coordinate. So I just need to ensure that the largest possible thing that does that ends up coinciding when b is 1. So I'm taking the maximum. So this is my definition for this GCD tilde. Okay, so I'm looking for the largest number that divides the x coordinate, whose bth power divides the y. And then the result is almost identical. A point is, and now we were clever, be visible. Ha ha ha. It's like, yeah. Okay, anyways, if and only if this new GCD was 1. So you see how the results end up being the same? All we changed was, now this is this new GCD version, and now instead of just visible, we have a B that shows up. So what's the next question? So now we know how to characterize when a point is visible or invisible. What's the next question? Now I'll ask you and tease you. What's the next question? What proportion of the lattice is visible, okay, or invisible? So here's the picture that I showed you before. So that's when B is 1, the straight line. And now, again, 50-50. And we know that about 60% is the stuff we can see. All right? Now let me put a 2 inside of here, this invisible. Again, 50-50. So look at how much we lost. What does this mean? Can I see more or can I see less? What am I coloring? I'm coloring the invisible things. So less means I can see more, which makes sense because now you can kind of see around things, right? With a straight line, I might not see something behind there, but with a curvy line, I might be able to see it. So with parabolas, I can see a lot more of the lattice. What do you think happens with cubics? I forget how far this goes. That was it. Okay. So now way less, right? It's invisible. So the question is exactly what Ben said. Well, what's the proportion? And notice how the numbers changed. So we went, 38% is hidden, 16% is hidden, 7%, 3%. Number theorists, do you recognize those values? I gave it away because I showed the next slide. So you're saying yes, but I think before you would have said no. Admit it. Okay, all right, so I got there, so he cheated. Okay, that's all I'm saying. Okay, all right, so as B increased, the proportion of invisible points decreased, meaning you can see a lot more the curvier your curves. Okay, kind of fun. So now it actually correlates very beautifully with the reciprocals of the Riemann zeta function. Here's the table. So if I look at this function and I look at the reciprocal, look at these numbers. Okay, that's the one, for regular lattice point visibility with the straight lines. But now if you look at these, okay, so those numbers are there, but look, 0.16, approximately what we were seeing in our 50 by 50 grid, about what we were seeing in our 50 by 50 grid, right? You see how they're off by 1? So when B is 1, you sort of land at, when B is 2, you land at this number here, when B is 2, but the exponent was linear. So the main result ends up being that if I look at the proportion of points that are B visible, all I need to do is look at 1 over the Riemann zeta function evaluated at B plus 1. So if you said B equal to 1, that's where you end up getting the 6 over pi squared, right? And if B is 2, you end up getting the sum, whatever value we got before. So that was the main result. Now, the really cool thing is that as B approaches infinity, that means you can see everything, which makes sense. It's like you can have the curviest of curves. And for those that care, right, the reason that this works out so nicely, the proof involves this beautiful identity by Euler that connects this, the Riemann zeta function and this product of over the primes. And so, I can tell you more about that if you want, but we also wrote it up, and you can, take a little bit longer to digest. But the idea was, what happens if instead of straight lines, it's curvy? Okay. So questions. I'm happy to also answer questions as we go. How are we doing? Okay. Yes, question.
Where did you get the Riemann zeta function from?
Oh, so I love this question. Okay, so we knew the result for the straight lines. We knew that it had to do with the Riemann zeta function evaluated at 2. So that we knew from the literature. And then when we did all of this kind of experimental evidence, like when we did the programming, and we saw these numbers, the natural thing became, oh, maybe, just maybe, they have something to do with the Riemann zeta function, because we knew in the linear case it had to do with it, and we just got so lucky. Like, the math was just beautiful. Like, there was no reason to expect that this should work when we went to a quadratic or a cubic. But the data, even in this very small grid, like 50 by 50, the data was so close to this that then it indicated to us that it was not coincidence, right? And right now, they only approximated to like 3 decimal places. Edre ran more code, and we had very strong evidence to believe that this was going to be exactly that value. But yeah, great question. So this was really, again, and we talked about this earlier at the other talk, right? It's like there's a lot of computation that kind of goes behind having a little bit of intuition on some previous case and seeing if you can generalize. Yeah, great question. Any others? Okay. All right, so one of the things that I think a lot about when I solve a math problem is you should go tell people about it, right? And so writing manuscripts is part of being a mathematician, although I remember as I was finishing my undergrad, I turned in my last essay, for this culture of something or other class. I was just like, I'm over it. And I turned it in, and I remember saying to the teacher, or the professor, never again will I have to write anything. And I was like, I eat my words every day that I'm writing. But writing and sharing your findings is such an important part of being a mathematician, but also getting, invited to give talks. You get to share about the cool things that you do for fun. And so as you're a student and you're thinking about solving problems, what might that look like for you? So it might be your thesis. It might be a project you do during the summer. It might be your homework, right? Find somebody else and explain it to somebody. When you explain something to somebody, you learn it so much better than really when you think you know it, right? So keep giving talks. The other thing that I really love about sharing my math is that all of a sudden people will ask me questions. And here's one question that I got asked. Well, I'll tell you in a second. But people will tell you questions, and you might be like, huh, I hadn't thought of that, right? Just like Abba, when I was like, what happens if you do Kirby? And all of a sudden, that's how you build a collaboration. And so the one thing is, if they're good questions, okay, maybe you yourself know the answer. Or if they're great questions, you might not know the answer, but it gives you, again, an opportunity to work on a research project, right? So ask a lot of questions. Okay, so here's what people asked me as I was giving this talk. So somebody said to me, why did you restrict the exponent to be a whole number? You heard him, the number theorist in the room? Yeah, why? Because it's interesting, right? Like, why? Why did you make that restriction? And honestly, it was like, because that was the first thing we thought of. So then somebody asked me this, and then I was like, again, because I said I don't like working by myself, I was like, Mo, we should think about this project. It's super cool. Let me tell you about lattice point visibility. And Mo was like, yeah, let's work on this. And so all of a sudden, Mo and I solved the exact same problem. Now, I gotta be honest, like, there's some weird choices we had to make about where we place the eyeball, right? Because, if it's rational, it might not go through the origin. Anyways, so there was like some technical things that are in there, but we were able to figure out, and guess what makes a comeback, right? We end up getting, again, something to do with the Riemann zeta function showing up and giving us proportion of visible points. Another thing that somebody asked me, they said, well, why are you only on the lattice? And I was like, why are we only on like 2 dimensions? What if we were in 3 dimensions or n dimensions? And so cue in more friends. So then I'm like, Carol, do you know about lattice point visibility? And she's like, I don't, but I have a student who might like this. And so then we started working with Santiago, who's now he's in Canada, Waterloo, working on his PhD. So we generalized our work to n dimensions with the rational exponents. So you see how very small tweaks led to like a whole new project? That's how we come up with problems. Okay, how are we doing? Okay. What have you learned? What have you learned? When you need a new problem, what are like small tweaks you can make? Change the domain. Why is something a natural number? Why is it only 2 dimensions? Yeah? Can you ask those same questions about probably everything you've been thinking about recently? Or something similar? No? Yeah, yes, maybe? You're like, but not yet? Yeah. So first you solve the thing that you're working on, right? You saw we didn't start with the rational exponent and dimensions. That's not how the story went, right? The story went, we go from linear functions on the plane to parabolas. That's how I started the question, and then we went from there, okay? So you start incrementing small little changes. So let me tell you about parking functions. Okay, now, I love this. How many people know about parking functions? Raise your hands. That's getting better. We're like at 70% or so, whereas earlier today it was like 5%. Okay, great. Okay, so now question, no, I'm just kidding. I'm not gonna test you. Okay, so for those of you that weren't at the earlier talk, let me give you a quick recap. So parking functions are, you have a queue of n cars entering a one-way street, okay? And they all have a preference. So they're gonna go to their preferred spot, and they're gonna try to park there, and if the spot is available, they take it. If not, they continue down the one-way street trying to find the next available parking spot, okay? And the question becomes, if I give you the list of preferences for the cars, their spots that are preferred, can all the cars park if they have to follow this rule? So if so, they all can park given that list of preferences. We call it a parking function. That's basically it. But the best thing to do is just to see it in an example. So same example, I'm sorry. So 113, making slides is hard, right? Ticks is awful. Someday I'll have a nice little program that'll do this for me. But okay, so 113, the first one is the preference for car 1. So car 1 enters the street. It's always lucky it parks where it wants because it arrived early. Car 2 also prefers spot 1, but that one's occupied. So it'll continue down the street, parking in the next available. So it takes spot 2. Car 3 prefers spot 3. It's available. It parks there. So we found a parking function. Okay? And then I made the same change here as before. So now car 1 wants spot 3. It's available. It takes it. Car 2 wants spot 1. It's available. It takes it. And now we're in trouble because, again, car 3 wants spot 3, but that was taken by car 1. So not a parking function. Okay, so sometimes you have parking functions, sometimes you don't. And now you know what's the question to ask? How many? Yes, how many? Okay, and then I told you, Henry Pollack has this beautiful proof that once I understand and then I don't. And so, it's always humbling to read things that I once understood and then read them again to only realize I'm getting dumber as I get older. It's wonderful. So then you have to check out the 2 articles that we wrote in Gross Angle Bulletin, because anytime I need to see this proof, I just go there, right? Where there's a little bit more exposition. Okay, so now I told you some of the story as the question and answer happened in the last talk. So Allison Baumgartner was a student of Katie Johnson at Florida Gulf Coast University. And I mentioned that they do this thing called an honors project. And so in their project, you have to develop 3 research questions. Now, this is kind of intense because they actually have to dig in the literature to find out something that hasn't been solved. It's not like they just go to a paper and find an open problem from somewhere and just copy it. And so they have to learn enough mathematics on their own to find a new question or develop a new question. So Allison was working with Katie, and Katie had taught them a little bit about parking functions. And so she went down that rabbit hole and said, okay, what happens if instead, when a car finds their preferred parking spot taken, the car just decides to back up? They just back up, try to parallel park. And then if that's taken, then you continue forward. So she asked this question, and she called them Naples parking functions. And so let's look at an example. So 313 was the thing that was not a parking function. We've gone through the parking function process, and we noticed it was not. However, when I look under the Naples parking, car 1 wants spot 3, it takes it. Car 2 wants spot 1, it takes it. And now here's where we were in trouble before, because car 3 would go to spot 3, and it was not allowed to back up under the classical rule. However, under the Naples rule, if this is occupied, car 3 gets to back into the spot. So something that used to not work now works by virtue of allowing it to back up, okay? All right, so again, note, not a parking function. So we now have a superset, right? Everything that was a parking function, is it a Naples parking function, was the first question. And the answer is yes, because if you can park without having to back up, then you should be able to park when you're allowed to back up, okay? So that's gonna be the proof of a statement I'll put up next. So what happened is, Allison gave me this question because she decided, she repeated that process of coming up with an open problem 3 times, and she decided to work on a graph domination problem. And so she said, I know you like parking functions, maybe you and your students can work on this during the summer. And so at that point, I was the director for MSRI up that summer, 2019. And so I showed the students as much as I just showed you. That's literally all I showed them. And I said, go forth and solve the problem during 6 weeks. I gave them nothing else. And they did. So this is Sakaya, Alex, and Andres, and then the mentoring team in the back. And we wrote this entire paper called The Generalization of Parking Functions with Backwards Movement. Also, I don't know, but if you know, but Electronic Journal of Combinatorics, good journal, right? So when people say to me oh, it's done by undergraduates, and I'm like, that's rude. What is that? They did good math, right? And then I don't know what the right word, I compare it to, I said, replace the word undergraduates and put women. Does that feel terrible? Then it's the same thing. If you say, oh, it's an undergraduate research, it's a women's we wouldn't say that, okay? Undergraduate mathematicians are amazing mathematicians. They're also not jaded, right? The older I get, I'm the partition function, impossible, right? And then an undergraduate comes by and they're like, well, if we impose these conditions, all of a sudden I have a solution. And I'm like, you're brilliant, right? So you should always do mathematics no matter what stage of your career. Okay, so let me tell you what other questions we asked. So along the way, we solved that problem, published it, and then we asked this question. What if the cars have varying lengths? And actually somebody asked that earlier, right? At the end of the talk. Somebody else asked, what if the even number cars can back up but the aughts cannot. And I was like, oh, that's cool. What if some construction occurred overnight and now the cars cannot park in those spots that are under construction? And then somebody said, wait a minute, what if you flip a coin to determine the direction of the movement? So you go to your spot, it's occupied, flip coin, go forward, flip coin, get heads or whatever, right, in one direction. Okay, great. So these are understood in some sense. So these are called parking sequences. And there's a new version I should add to this, which is parking assortments. I can tell you more about that. And then this one is some new work that's currently being done at California State University East Bay. They reached out and they asked me that question. I was like, I don't know, but you should figure it out. And so they're working on that. And then these ones where construction occurs overnight, they're called parking completions. So we've done that. And then this flip a coin to determine this started, we have a paper that we just put out not too long ago. And then Enrique Treviño, an undergraduate student, also worked on this and published a paper. And so these have been questions that we get during talks, questions that students develop, and it leads to really meaningful mathematics. So really the change is you just ask, like, what if instead of a linear, you use a quadratic? What if instead of the cars having unit length, they have longer lengths? So it's this constant, like, what if? Okay. And in fact, these students asked so many questions that we wrote an entire article. Do you know these choose your own adventure books? Did you ever read these as a kid, right? Where you go to, like, you're somewhere in the story and then you have to make a choice. Fight the dragon, go to page 73. Oh, run away, go to page 20. And you're going like back and forth. And most of the time you end up at a dead end and you have to start over. Okay, so we wrote an entire article using that premise. And so you, as the reader, get to make choices about your style of parking functions. And then you get to a point where we tell you, oh, this has been considered in this work, or brand new problem. It has yet to appear in the literature. And so, we then trace all the possibilities, and in the back, if you don't really want to read, but I hope you do, because there's also really wonderful illustrations that my sister did. But you can just read the back of the article, and it has a table with open problems. So this is the second paper, that group of, so you should see some familiar faces. So Sakaya, Alex, and Andres came to visit me at Williams, and with my colleague, Josh Carlson, we wrote that article. Okay, we can do it. Let me show you the thing that gives me joy. Okay, multiplex juggling sequences. I don't assume that you've ever seen these things. Have you seen these things? But you've seen multiplex? Yeah? Oh, well, let me show you. Okay, so here's what we're gonna do. So this is like lots of, math, but let me just show you a picture, right? Because like I could say it very formally, or I could just tell you the objects. Okay, so I'm gonna think of juggling in a different way, so forgive me. I'm gonna think of like these conveyor belts, okay? Because I wanna keep track of the height of the objects. So I'm gonna put some objects, they're all indistinguishable. I can't tell them apart, so they're just, these objects. And I'm gonna say at height 1, so notice that I have this kind of bucket in this conveyor belt. At height 1, I have 2 objects. At height 2, I have 1 object. At height 3, I have 1 object. Okay? This is what we call a juggling state. So just some distribution of the objects that you have into these buckets. That's it, juggling state. Now you're gonna put these together. Okay? So here's how I'm gonna do it. I need to put juggling states together, so I need to give you some rules. So let's suppose that we start with this smaller example. So 1 object in the bottom, 1 object at height 2. 1 time step later, all of the buckets will lower by 1 unit. Because I have an object in this one, it's gonna be in my hand. And jugglers, you don't like keeping the object there. So immediately you're gonna redistribute it somewhere. So I made this choice. So follow me here. I took, first off, one of these, I can't tell which one, but it's the one that used to be at height 2. Because that bucket lowered, so there was already an object there. And the object that came to my hand, I happened to just put in that same bucket. Are we okay with that? So that's the rules of the game. So now, at the next time step, I will have 2 objects at hand, and I get to redistribute them in some way. So I'm gonna redistribute them like this. I made a choice. There's many choices to be made. That's the choice I made. How are we doing? Okay? Now, at the next step, I have no choice because I have no object to redistribute. So they just lower by 1. Okay? This is what we call a multiplex juggling sequence, okay? So the game now is always a counting question. So I want to count. I give you some starting state, meaning, say, for example, one object at the bottom, one object at height 2. I give you some ending state. In this case, I pick the end and the start to be the same. I give you some length, meaning the number of time steps that passed. So from here to here, 1 time step, 2, 3 time steps. Okay, so you don't count the pictures, you count one less, because it's in between the pictures. Okay, so I give you all of that. So the starting state, the ending state, the length of the sequence or time, and then there's times where I actually set a limit to how many objects I can put in any bucket. We call that hand capacity, because it makes sense. Like you can't hold 100 things, right? Unless they're tiny. So in this case, you can set that parameter or not. Most of the time I'll ignore it. But there's good math there. You might limit that and get new results. Okay, so now I'm gonna just do an about face and be like, let me tell you about this other thing that seems completely unrelated, but remember, I already told you that they're the same thing, okay? So one of the things that I absolutely love is vector partition functions. So let me tell you how the game goes. I'm gonna give you a matrix, and I look at very particular matrices, but I'm just like sweeping that under the rug, okay? So I'm gonna give you a matrix, say for example, A, and then I give you a vector in the column space of A. I hope that means something to some of you, okay? Which is really just, can I write that vector B as a linear combination of the columns of the matrix, right? But I'm restricting so that the weights, what you're used to calling the weights, so the multiples of those columns, have to be non-negative integers. So if you use a column, you can use it 0 times, 1 time, 2 times, 3 times, 4 times, and so on, okay? So you can't use column 1/2 times. It has to be a whole number, okay? 0 onward. So the question then becomes, if I give you a matrix and I give you a vector in this column space, in how many different ways can you express B as a linear combination of the columns of A? And again, linear, I mean non-negative integer linear, but I get lazy, right? It's like a mouthful, okay? But again, how many ways can I write B? As a sum of the columns of the matrix. All right, so that's what we call a vector partition function, right? Which sort of generalizes integer partitions. It's slightly different. Okay, so let me show you one option here. Now, you also can just completely forget about the matrix, and you can turn it more into just a combinatorial game. So I have some vector alpha 1, some vector alpha 2, and the objects, so this is for the exact same thing here. So notice alpha 1 is a column, alpha 2 is a column, and I'm gonna take something that's linearly dependent, okay? Linearly dependent. So I add these previous columns to get the third. Yeah? So you see this column plus this column is the third column. Why do I need linear dependence? Come on, one mathematician in here, tell me. Yeah, because if the columns are linearly independent, how many solutions will your system have? Okay, everybody doing it with the finger, but nobody saying a word, because God forbid you might be wrong. 0 or 1, okay? Okay, all right, great, okay. So that's not that interesting, right? Like if I want to count, I want to be able to have not just one way to do it. Like I want there to be some meat, okay? So I strictly put in some linear dependence at the end of the column so that there's some interesting things. But notice, really what I'm using is alpha 1, alpha 2, and then the sum. So the proof here says, okay, you tell me some vector B that's a multiple of alpha 1 plus a multiple of alpha 2, and then how many ways could you write it as a sum of alpha 1, alpha 2, and then this new vector alpha 1 plus alpha 2? And the answer ends up being, well, which of these two numbers was smaller? Because that restricts how many alpha 1 plus 2 columns I can use. And so you can use this thing as, at a maximum, the smaller of the two numbers, okay? Because you can't use negatives as the weights. So you take the smaller of those two numbers, and then it might be that you don't use any of these, and that's where you get the plus 1. So there's times where you get these beautiful formulas that involve minimums to solve that question of how many ways can you write B as a linear combination of the columns of the matrix. Okay, so one of the things that I noticed as I was working on these vector partition function problems is the following. So here's the 3 vector partitions of this vector 2 alpha 1 plus 2 alpha 2. Now, these are multi-sets because I need to count those elements with multiplicity, right? So I wouldn't think of this as just alpha 1, alpha 2. I'm actually thinking of I need to keep track because if I add this plus this plus this plus this, I do get that. Or I could have done this plus this plus this, and I would get that. Or this plus this. Oh, sorry. This one together with this one, give me that one. So you see how those are, I need to keep track of how many times that element shows up so I can see the 2 when I add. Okay, so I got 3 vector partitions for this vector. And then I was like, there's 3 multiplex juggling sequences that start and end with the 2 objects at the bottom bucket. The hand capacity is set to 2. And I do it in length 2. And of course, like, this is ridiculous. Like, I found 3 apples and 3 oranges, and I'm like, are all apples oranges? Right? Like, okay, all right. So I was like, is this just a coincidence? It is not. And you go into the OEIS, right? The Online Encyclopedia of Integer Sequences. And I started doing other experiments. And I said, what happens if I input, remember I have a lot of linear dependence, so I have this column where I add all the first n columns, and I just multiplied that by 3. And I said, in how many ways can I write that vector B as a linear combination of the columns of the matrix? And the answer I was getting as I varied n, so I started n equals 1, 2, 3, and so on, was this sequence of numbers. And notice the description. Number of multiplex juggling sequences of length n, there's an n there, base state 3, there's a 3 there, hand capacity 3. And now I'm excited because I'm like, maybe there's more to it than what I first saw initially. And in fact, we kept getting this over and over again. Every time I kept doing some vector partition function problem, I would put it into OEIS and it was like, multiplex juggling sequences with da-da-da-da-da. And at some point I was like, fine, I'll learn what these things are. They're haunting me, but I won't do it alone. So, all players. So you see Caro again, Christopher Hanusa, Alejandro Morales, and Anthony Simpson, who was one of my students at Williams, who, I adore. I was like, let me show you this problem. If we do it, I think we could solve it together. Okay, so here's what we found. We found that, in fact, it was exactly the same thing. And there's a way to do this. So here's the result, right? One small result in what happens all of the time, okay? So I'm just giving you like a taste of it. So remember we saw, I'm sorry, I changed letters. This used to be an N in that previous slide, my apologies. So now it's an R, and then N for the multiple. The number of those vector partitions is the same thing as multiplex juggling sequences. So the multiple here turns into the starting state and the ending state, and also the time, and R goes into the hand capacity. So I can just line them up, and these are the same problem. And the way that this happens is when I look at the picture of this juggling sequence, I just need to keep track of when I made a toss and to what height. And so every time I had a picture, I could encode the height and the time at which I threw the object, and that corresponded precisely to a vector or a column in the matrix that I would use in the vector partition. So it's easier to see when you look at this particular article, so I'm not going through all the details. But again, this was sort of the key insight, that every time I made a toss to a particular height, that encoded a column in my matrix that then appeared in the partition. And vice versa. If I knew what column I was using, I could decode it by figuring out when I threw an object and to what height. And so all of a sudden you get this beautiful bijection between vector partitions and the juggling, which was like completely unexpected. And I should tell you, when Anthony came to my office one day, and he said, yeah, I figured it out. And I was like, okay. And I was like, so how does it work? And he's like, yeah, you just keep track of when you toss and to what height. And I was like, wait, what? And then he said it like 10 times, and I was like, it doesn't work that way. Like, there's no way. That's so clean. And then we had to do like 3, 4 examples, and I was like, oh my God, you might have figured it out. And we did this for those that are interested. We also did this for other Lie types. So we did it for all the classical Lie types. It got very involved, but it's possible to do. But I mentioned this earlier. I'm a big proponent of writing your math in a way that's accessible to others, especially younger folks. So one of my other students, Maria Rodriguez Hertz, and I wrote 2 articles about this topic. So the juggling stuff, the multiplex juggling, and then its connection to the cost and partition function. And it details exactly this proof, like very, very detailed so that I hope we made it so that you can follow all of the steps and then, check them out. These are freely available online. And then for those of you that want to see a lot of the other cases, you can check out the, more technical reference. Okay, now what are the new questions that came up? So one of the things that were really interesting is that we started thinking about average behavior. Like on average, how many tosses do you make as a juggler? Right, you're over here juggling, and say 10 minutes passed. But then next day you juggle for 10 minutes, and then the next day 10 minutes. On average, how many tosses do you make? That's a good question, right? Like you want to know how tired you're going to be, okay? So that you can have an expectation of whether you should take a rest day. Probably take a rest day, because Ben has like juggling objects that are like 4 pounds each. It's terrifying, Anyways, you're working out hard. So one of the things that we started thinking about is like, well, what if we start like limiting the height? How many ways could we write, or how many juggling sequences are there? And on average, what is that behavior like? And so that's some of the work that I've started with Steve Butler and Alejandro Morales. But here's some advice to conclude. Advice for students who did not ask for it. So, I'm sorry. We love, me as an older person, I love giving advice, but I also recognize that you did not ask for this. So I apologize in advance for giving you unsolicited advice. So one of the things is that absolutely apply to go to research experiences. That also is for graduate students and postdocs. The Graduate Research Workshop and Combinatorics is precisely the space to come and do some math in a collaborative space. People are super friendly and we just hang out and do math. So it's like the equivalent of an REU, and you don't have to commit 8 or 10 weeks of your summer, it's 2 weeks. It'll be in Milwaukee. So please, please apply, come hang out and do math with me. And the key is for you to just keep asking, well, what if we do this other thing, right? Keep asking, what if we just change this parameter? And then the other thing is, as you're applying for these opportunities, start early, because a lot of them are super competitive. And so you wanna make sure that you start getting your applications ready and get some feedback from your professors. And then also don't wait to go elsewhere to do research. You have phenomenal faculty here who I guarantee you are eager to talk to you about their math, right? Like they live for it. So go ask them what they're working on and if they might have a project that you can collaborate with them on. And then the other thing is, you wanna build strong relationship with your professors. And so start going to talk to them about their research, because they'll just talk to you for an hour and you don't even have to pay attention. You can just be like, and they'll just keep talking until you're like, okay, I got class, right? But you're building a relationship with them because at some point you're gonna need some letters of rec. And it's much easier for me to write a letter of recommendation for a student who's come to talk to me and I get to know them better than just a student in my class. So check out also, if you are looking for programs, Steve Butler gets this awesome website up every year that he updates. So mathreuprograms.org. I'm gonna nudge him so he starts putting in other opportunities for graduate students and postdocs. But that is my summary here. So what's math research? You're just identifying questions and working on them. You're constantly asking what if questions. I do that anytime I go to a talk. I do that anytime I read a paper. I basically do that all the time, right? Like, what if you do this other thing? And then, try to build collaborations. I find personally the math is much more fun when I have fun people to think math with. So I hope you enjoy some new mathematical adventures of your own. Thank you.
Any questions?
Yeah.
I guess like with the coin toss.
Yes.
That was the first thing I was thinking. I wasn't thinking about the coin toss, but what if like a bad person can always decide what happens? So it's kind of similar.
Oh, like adversary punching functions.
I guess so. You guys, like, is it likely to, like, I know it's ongoing work, but is it still going to, are parking functions still always going to be like adversarial parking functions or like random parking functions and you always cost the coin?
Yes, because the way that it got done is they think of them almost as being on a circle.
Okay.
And then so eventually you will park.
But then what's the point of question about it?
Oh, no, sorry. Okay, I won't back up. No, sorry. I'm thinking about something else. So you have a one-way street. You go to your preferred spot. If occupied, you flip a coin, or with some probability you move forward, and with some probability you move right. And I think it was like, what is the, it was like on average, what is the behavior of this? Like what proportion of these sort of trials would lead you to be able to park?
Wait, you go left the whole way, or you just...
No, you go left. Oh, this is better.
You go left one and then you go right?
No, you go left all the way until you find a parking spot.
Okay.
And then if it's heads, you go continue forward until if you find a parking spot. And then if it's 1 minus P, you go left to the start of the street.
Okay.
Yeah.
I was thinking about what if it's a 50% chance to go back off one. And then go forward again.
Yeah, that one is not done.
Okay, well,
That one is not done. Yeah, and we were talking about earlier, was that you? Yes. Yeah, we were talking about what happens if you not only do that, but you limit how far back you can go and how far forward you can go, so that you introduce two new parameters. So from your preference, maybe you're willing to go forward 5, because it's much easier to park like when you go in, right? And maybe you can only back up 3, because that's probably too far to back up if you go any more than 2 or 3 spots, right? So that you could also introduce some like new parameters on how much you're willing to go back and how much you're willing to go forward, in addition to the probability question. Yeah, so like all of those tweaks, you're asking the right questions because I don't know the answers. Like I don't know what happens.
Actually, I have 2 questions.
Okay.
The first one is math related. So actually, I was in a talk early afternoon, and I thought about the formula and the number of parking functions. The more I thought about it, I just, found that it's very similar to the Kelly's formula for the number of trees on the label vertices. There's any like simple explanation for?
For the bijection onto trees?
Yes.
I don't actually remember this proof, but yes, there is. And I think you want to read the work of Gessel and So have a proof that uses trees and like tree inversions, and a statistic called the lead, I think, if somebody remembers. I'm looking at the profs. I don't know if y'all remember. Like this work with trees, how you biject from trees.
There's a bijection, I don't remember.
I don't remember, but I think it has something to do with like a particular statistic. And I think it has to do, in the Gessel and So paper, they enumerate by counting the number of lucky cars, which is the number of cars who actually park in the spot they preferred. And that, I think, had something to do with some statistic, and I believe the word is a lead in a tree. And so they were able to not only do this bijection, but in fact, they do it in a way that preserves a particular statistic, a discrete statistic on the objects. Yeah.
Is it okay we can chat a little bit more?
Absolutely.
So my second question is, you talk about how we find new problems to work on. So my question is, how do you know that the problem you find is the right problem?
Oh, I never know.
Okay.
I mean, first off, I think, in my opinion, there is no such thing as the right problem. I think the right problem is the one that you're interested in, right?
So if you find a problem that you're interested in, and like you start working on it, and you work on it for a while, and you get stuck, then what would you do?
I love this question, because I say it to my students every single time in class, okay? Because I'm running a research course, and we have been stuck on the same problem for 8 weeks. Something very easy to state, okay? And I will tell you in a second what it is. You impose more conditions. At least in combinatorics, what I have found is that if I start with a set of objects, and I want to count them, right? That's always my question. Here's some objects with some properties, and I want to know how many there are. If I just cannot get a handle on that count, the first thing I do is I check OEIS, yeah? And I'm like, have these numbers been found before? 2 things will happen. One, yes, they have been found before, and then you'll get some description of another set of objects, or maybe the same set of objects are described there and you know somebody's done it, okay? The second thing that can happen, and if that happens and your thing is not described in there, then you try to find some bijection to a set of objects that are described by that sequence, and then you know the enumeration comes for free, okay? So win situation in my book. The other situation is it doesn't show up. That doesn't mean you quit, right? That doesn't mean you quit, because you still try to enumerate them, and now you get to add a new sequence into the OEIS, okay? But I understand. That feels a little bit shaky ground, because you may never be able to, enumerate them. You might just have a lot of data, and you don't see the pattern, and you don't know how to find the answer. So the thing that you then do is you make your set smaller by imposing some additional conditions. And you try to keep adding conditions, until the set hopefully gets small enough and it has a lot more structure. Do you see what I'm saying? Like by imposing a condition, you're giving it a lot more structure, which means there's less of them. And you do that and then you repeat at every step. Add condition, check against OEIS. Did I get a hit? Yes, biject. And then try to remove the condition to see if you can enumerate. Otherwise, no hit. Can I enumerate directly? No. Continue, add a new condition. And you iterate this until something good works. This has yet to let me down, and I am going up for full professor as we speak, okay? I've made a career by doing exactly this. No, it's a great question, right? And honestly, the best thing is don't quit. Like there is a point where something gets really hard, and it feels really demoralizing, because you've been thinking about this project for so long. But this is why I like having friends to do math with. Because it's not about did we solve the problem, it's about did we have fun while we were together. And a lot of the times I don't even know how we do all the math that we do, because half the time we're laughing. Like seriously, like, oh, that was dumb. Okay, let's try again. And we're just like giving each other props when something works, and we don't feel bad when something doesn't work.
Any other questions?
Yeah.
Is the parking function like that all the cars get the spot that they want, or all the cars get a spot?
All the cars get a spot. Yeah, and so there's cases where they all get what they want, so everybody prefers a different thing, and there's cases where only one car gets what it wants. So if everybody prefers that first spot, the first car gets it, because it was the first car in queue, and all the other ones just keep going into the next spot's very unhappy. Yeah, and so there's that number of cars that are getting what they want. That's what in the literature is called the number of lucky cars of a parking function. And so this is what's related to the question he was asking about these other objects called trees.